No.
We are live on YouTube and LinkedIn.
All
Our
right.
topic today is nuclear waste could be the game changer to unlimited electricity. It's a pleasure to have three great professionals today with us: Ronald Stein, Oliver Hermers, and Steve Curtis. Uh, you can stop the video later and read their short bios carefully. Strong bios, fantastic. Good evening, my friends. How are you going?
Hello,
Excellent.
Armando.
Fantastic.
Good. Thanks.
uh, Based on your article you wrote together, I suppose, nuclear waste is not waste. There is still energy in it. How how this works? I'm not aware about this. Could explain to us?
Let me give the simple explanation, and then
Sure.
Steve and Oliver can give you the detailed explanation. The water-cooled reactors, which is the basis of the reactors in the world, of which there's about 440 in the world, is based on technology that can take that fuel and only extract 3% of its capacity. And it's just like having the strength to squeeze an orange. You know, a baby can't squeeze an orange, maybe get a little bit out of it, and then they're done. But if you get a gorilla, you can squeeze the whole thing. Um, Basically, the fact that we've taken out 3% of the energy, it is so-called slightly used nuclear fuel. The new technology of fast breeder reactors can squeeze the rest of the juice out of it, and that's the unlimited electricity that's available. So we are basically dealing with all the reactors in the world right now are water cooled and just using a little bit of the energy available from the fuel that we're providing it. And I'll let Steve and Oliver give you some more detailed explanation on that.
Yeah, and you mentioned a 3%,
Yes.
Yeah.
only 3%, Oliver.
Yeah.
This.
Only 3%. Yeah. What happened is that these old reactors, or the technology that was designed for the last 60, 70 years for commercial nuclear power, is the isotopes that are used for power production. And they're optimized for very specific isotopes, the isotope, the 235 of the uranium. And most of the uranium in a nuclear power reactor is uranium 238. And the uranium 238 in the design process for this type of reactor cannot be used to make energy. And they use only the couple of percent of enriched uranium 235 in the fuel, and therefore they can only get the energy out of that isotope. Now, new reactor technology, which is actually old reactor technology because it was already developed beforehand in the 1940s, they actually can split everything, all the actinides, but they use a process called breeding to effectively turn whatever is not easily fissionable into fissionable materials, and therefore you can effectively burn up the entire fuel that you have, the remaining 97%. And that's the idea behind a lot of new reactor companies that are starting up to take the spent or very slightly spent fuel and turn that into energy. And since you can get 30 times more energy out of than in the first fuel cycle, there's a tremendous amount of energy sitting in storage right now that can be utilized for electricity production. So, Steve, any?
Yeah,
Oh, yeah.
before you go,
There's a lot of people that claim that economics is going to play a role in this.
Uh-huh.
And that's that could be made to be true, I suppose, if you think of it in some perspectives. But the perspective I like to do it is if we come at this from the free enterprise direction and perspective, then it really doesn't matter what the cost is because people will buy the cheapest energy. And so if the guys can't make it work, then they'll go buy energy from something else. But the fact is that they've already made this work. There's already at least 7 or 8 companies incorporated and privately invested to make this part of it work. They're looking at radioisotopes now, the use of radioisotopes for other applications in medical and other parts of science. But when you split the atom, you get 50 million times more energy than when you burn one molecule of coal. That's a huge advantage. I don't think we should ignore. So the whole line is, if you know, kind of like my mom used to say, waste not, want not. So they can mine uranium till they're blue in the face and stack this stuff all up to the rafters. We say, why not use it? Why bother the earth when you don't have to? And the machines are there, the technology's there, the capability's there. We just have to have the impetus to do it. And I really don't think people see this perspective of how powerful this system can be. And basically, if you're going to want to dispose of all your spent fuel, slightly used nuclear fuel, we call it, then you're going to want to burn up electricity as fast as you can. So if you're fissioning these things, you're going to want to get them to fission as fast as you can. So you're going to encourage people to use more electricity and basically get it down to a penny kilowatt hour, you know, because that's the way you can get rid of it all. And as Oliver figured out, the fission products, even the fission products that are left over, are mostly rare earths and platinum group metals that are really, really valuable. So you do have to let them sit for about 50 or 60 years. But there's no point in throwing all this away. I mean, we're really cutting off our nose to spite our face. And a good analogy is the way the Native Americans used the buffalo. When they captured buffalo, they used all the buffalo, hooves, everything, skin, pelts, the whole thing. When Americans harvested buffalo, they cut out the tongues and the horns and left them to rot in the field. So I think we should really be conservative minded. If we're environmentalists and we're really conservative minded, this makes sense. On top of that, it's very economically profitable and beneficial.
Yeah. Let me see that George Oliveira from Portugal, Colonel George Oliveira. Welcome, George. Thank you for coming. What's the meaning of exactly slightly used nuclear fuel? What is it exactly? Who can answer?
Go ahead, Oliver, your turn.
Okay. Well, we coined the term slightly used nuclear fuel for the fuel that commercial light water reactors produced during their time of operation and energy production, because they only use 3% of the fuel and 97% of the fuel is left behind. So it's when you have a bunch of fuel and you know, let's say you have 100 pieces of coal for your coal oven and you use only 3 pieces, then whatever is left is a bit of ash and 97 pieces of coal, right? But you wouldn't call that trash or waste, right? You would say, why not burn the other coal as well, right? It's now for the nuclear, we get the clean energy advantage of not using coal, but it's the same thing. You have a lot of fuel left over, and you want to use it for electricity production. You don't call it waste, right? So we call it slightly used nuclear fuel, right?
Yeah, but Oliver, there is only one energy in the world that can leave not 97% of energy without using. It's impossible, Ronald. How can we live with this?
Yeah.
Well, you know, the interesting thing that's going on today is the government is spending billions of dollars subsidizing wind and solar. And the difference is wind and solar generate occasional electricity. It's not continuous, it's not interruptible, it's not dispatchable. And Steve brought up a fantastic point that the nuclear generated electricity is going to be very, very cheap and expensive. And besides not using natural resources like wind and solar, the nuclear is going to use very little natural resources and provide continuous, uninterruptible electricity, which is the way the world's going. We've got artificial intelligence, data centers, airports, hospitals. Everybody needs continuous electricity, and it's almost ironic and dumbfounding that we're spending billions of dollars to generate electricity whenever the weather conditions are right. That's
Yeah.
wrong direction.
Yeah. And Steve, the meaning of this conversation is that we have 97% waiting to be used, this energy waiting to be used. How can we do that? How can we recover this 97% remaining?
Well, technically, it's a lot simpler, and engineering-wise, it's a lot simpler than light water reactors, simply because you don't need the high pressures that you have to have the water at. The idea is you want to carry heat away. And if you're going to carry heat away with water, it boils at 212 degrees Fahrenheit. That's not a very big difference between input and output, so it's very inefficient. That way they have to put it under pressure. That way the water can carry more heat. But it still can only get up to about 300 or 400 degrees Fahrenheit. And let's take, for instance, molten salt. That melts at 500 degrees C, okay? So you have a much larger range of energy and heat that makes it more efficient, number one, and higher heat you need for stuff like making steel and things like that. There's a lot of chemical manufacturing needs a lot higher heat. So you don't have to turn it into electricity and turn the electricity back into high heat. You could just use the direct high heat. It's called process heat. So there's a lot of advantages to this. And there are some engineering nuances to it, of course, like everything else. But I think they've conquered them. I think they've overcome those. There's nothing left to discover to make this work. And really when you're making it, you don't need a lot of fancy new material. You can use almost off the shelf equipment to do it. And the construction with not the high pressures, it makes it a lot simpler to put this together. The trouble is nobody's built one for commercial yet. There's not been a commercial one built. So everybody knows when the first color TV set cost $100,000 and the ones after that cost, $500 each. And so part of what our idea is to drive that first of a kind construction so you can work out the commercialized things you need to work out with that first of a kind. We've already worked out the theoretical ones with the national lab. They actually ran one for 30 years in Idaho. That worked fine. It was a sodium cooled process called Experimental Breeder Reactor 2, and it ran for 30 years without a problem. And they did 2 experiments where they cut the external power and they cut the pumps for it off and just let it sit there without any intervention, and the whole core cooled down all by itself. So the safety, the economy, the simplicity, the easier to engineer things, the cheaper they're going to be. So we just need to find a way to make the first one of them. I think we're going to be on our way.
And Oliver, why is not being used this solution? Is there any specific reason?
Well, there's a lot of the opposition comes from different sides, including the industry and the power providers, the utilities. They are used to the light water reactor designs, and the light water reactor designs are known. They know how to service them. They know how to get the parts for them. They know how to operate them. When you introduce a new type of design into a system, you always start to kind of worry about, what can go wrong, what could be disruptive, until you kind of have a process that it goes automatically, right? I mean, interestingly enough, they forced it on us with the wind and solar, very different types of energy productions to the nuclear power plants or even coal and gas. And we see what the fallout was from that. So we don't expect it to be as bad as for wind and solar, but there are nuances that is from an economic point of view not preferentially treated as the old designs, even when the old designs are flawed. Nevertheless, the safety, the need to find a solution for the 90,000 metric tons of spent fuel that is sitting at various reactor sites is hopefully helping to convince some people to use the new designs of fast reactor recycling to implement those technologies. And those reactors, these are massive. They can produce up to 6 gigawatts, right? I mean, this is like 20 coal plants or 10 coal plants at least, right? So they're huge, and so they are going to drive entire grids, subgrids, right? So there is a benefit to have these big systems, and there's also some downside. So it is a process to slowly grow it into the existing grid system, but ultimately it will be the future. You can run the entire country on those systems eventually, and you can run it for hundreds of years without mining new uranium for those systems, right?
Armando, go ahead. I'm sorry, Oliver.
Yeah,
Let me just add a couple more things. There are some political implications to this as well.
All right.
Number one is subsidies.
Yeah.
And they subsidize the competitors of nuclear power much more than they subsidize the nuclear power development.
Why?
So that gives us because they have, I don't know, lobbyists and all whatever happens. I'm not the best guy to ask about politics and how it works in DC, but they do have that idea, and I think most of it is driven by lobbyists and businesses that are interested in that line of things. And the other thing is the Nuclear Regulatory Commission is not approving new reactors. They say they are. They say they're working on it, but they haven't really approved one. They've approved 2 in the last 30 years. Okay, and they've been in business since the 1970s. And they just don't have any sense of urgency to pull this off and make it happen. Again, why, you ask? It's a political question. They're not given the incentive to do that.
And this is something that Ronald can answer because he's a candidate for California candidate next term.
Governor. Well, let me elaborate on what Oliver was talking about. The utility companies, you have to take a look at their technical organization is all for water-cooled reactors. Now, these people have jobs, careers, looking for retirement. They don't want to change. It's not in their best interest to change. And so it's going to either be subsidies or, private development that's going to get this thing off the ground, because you have, if you're talking about over 400 reactors in place around the world, that's a lot of technical organizations throughout the world, all water cooled. And you want them to do a 180-degree about face? I don't think they're going to be too receptive to that. And then, the wind and solar, they're getting subsidies because they came on the forefront of being the only zero-emission electricity we can get. And so a lot of subsidies went that way. But as it turns out, the amount of material they're extracting from planet Earth is devastating the world, and then it's generating the most expensive electricity, and which is not good for the economy. So there's so many things that are going against wind and solar, and there's so many things for the fast breeder reactor that it's a matter of time. But who's going to basically jump out and be the first?
Let me point out one more thing, if I could.
Sorry.
Is that okay?
Go ahead, please.
Okay, because if you notice throughout history, when things transition, everything transitions to a new technology, right? But it does so very slowly. It's not like people are going to get fired from their jobs that are doing light water reactors. Light water reactors are good. They've just renewed one for another 20 years through 2050. So even if they don't build any more light water reactors, people are going to have nice and fine careers that are working on light water reactors as we bring in the new generation of people. And we should let industry do that. Industry should figure out the way that they're going to train their people and bring them along the way they need them to transition to new energy. It's like coal and natural gas. Okay, they were in a big hurry to get rid of it, and they haven't got rid of any of it. And so it's going to be a smooth transition, and people in free enterprise will figure it out as they use their systems to try to make their economic benefit work. And so it's not going to be a case where a lot of people are going to be losing their jobs overnight and having to worry about careers and everything. But if you let free enterprise take its course, everybody will get to a nice retirement. The new people will come in with the new technology. The new technology is not that much different from the old technology. I mean, I'd say 70% of a nuclear power reactor is electrical systems and mechanical systems and metallurgy and things like that are common to a bunch of different industries. So I don't think you're going to see a lot of people being devastated in their jobs or their careers.
Yeah, interesting. Professor Seppo Corpella has two comments. The first one is not the word, I cannot read very well here. I have several things. Who can help me?
Is not the worry about weapon grade fuel one of the reasons for the present method of using uranium?
Okay. Yeah.
I can take that on if you want me to. This is what they call proliferation.
Yeah.
Now, yeah, okay. These are not weapons grade reactors. These are, in fact, we're using uranium that's been very depleted in uranium-235. Proliferation comes when you're talking about weapons grade fuel, you're like 95% enriched in U-235. We're talking something about 1% enriched in U-235. And a lot of people think about plutonium. They're all worried about plutonium as a bomb fuel as well. But when you talk about the reactor grade plutonium that comes out of the spent fuel, it's not good for making bombs. It has too many higher level isotopes of plutonium. If you look at what North Korea did, they didn't take spent fuel and use that plutonium, which would have been far easier for them. They went and built their initial reactors and built their own weapons grade plutonium fuel with far less of the higher level isotopes, which means you leave it in the reactor far less time, pull out the almost pure 239, because you can't separate 239 from 240 and 241 and all those isotopes. So you have to pull it out of the reactor when it's still just uranium-239 without those contaminating isotopes. There's a lot of reasons in physics I can go into that, but the bottom line is nobody would try to use spent fuel uranium to make a bomb. It would just be too cumbersome, too awkward for them to do it. It'd be hard to make it work when they can go get plutonium-239 all on their own and just use it. So the proliferation, first of all, of weapons grade stuff is not an issue because there is no weapons grade stuff in spent nuclear fuel. And the other one about plutonium is it just simply can't be used. Can be, they've proven that it can be, but nobody would because it's so awkward and tough to make it happen.
And Ronald, this is for you. I see that there is solar and wind terms here, but I cannot read. Sorry. Who can help me?
Positive correlation between the amount of solar and wind and the price of electricity. Denmark and Germany lead the pack on expensive electricity, and California's right behind them.
Oliver, that's yours.
Germany was the first country to go green, and today they got the most expensive electricity in the world. And
wow.
I basically promote California's right behind them, and we have the most expensive electricity in the entire United States.
Now, Oliver studied Germany and what's happening over there. I think you have some insights there, Oliver.
I do have some insights, and it's a complex system that they have in Europe for, they have like an exchange for electricity Europe-wide, and they buy and sell electricity across Europe. And it's like a stock exchange for electricity. Germany runs a lot of times into the problem that they overproduce electricity through the day with wind and solar, and then they have to sell it at a negative price to its neighbors.
Wow.
And then at night, when they don't have enough, they have to buy it at a high price back from its neighbors. Because the neighbors are still having, the classical power production like nuclear and so on. So that's one aspect that drives the price up. The other aspect is that when they start building these massive wind farms, and you understand these wind farms are thousands of square miles big, right? Because you need so many wind turbines. You need transmission lines, new transmission lines from those wind farms to the people, to the cities. Usually in the past, you build a big power plant in a city and your transmission lines are fairly short. Now you have to go countrywide. Maybe it's in the Baltic Sea or the North Sea or wherever you need to run transmission lines. And those costs for these transmission lines have to be paid by the ratepayers as part of the electricity price. So there's different factors within the electricity price that adds costs to the kilowatt hours that you pay, and that drives the prices out. And the more wind and solar you have, the more the costs go up, right? When you don't have enough base load like nuclear that can smooth out variations in wind and solar. Germany is past that point. Germany has more wind turbines capacity than the whole country uses in electricity. They also have more solar panel capacity than the whole country uses in electricity. It is just these things don't produce anything, right? I mean, especially Germany in the winter, you produce like maybe 5% of your solar because the sun doesn't really shine much in the winter. And sometimes you even don't have wind in the winter. And then suddenly people want to stay warm, right? So they need electricity for all kinds of things. So the point is, then suddenly you have to import electricity from neighboring country, and that drives the cost up even higher because the other idea was to build backup power. So now you build windmills and solar panels, but you also build conventional power plants like gas power plants and so on, just so when the wind doesn't blow and the sun doesn't shine, that you have electricity. So they're building two systems in parallel. Of course, the price goes up when you have to build everything twice just to make sure your country doesn't go dark, right? So and so there are various factors in Germany and similar in Denmark that drives those costs up to the detriment to their neighbors. Sweden and Norway are ready to cut their power lines to Germany. Don't want to produce any, extra power for Germany because of their energy policies, right? So there's all kinds of heartburn going on, not just for the consumers in Germany for the price, but even the neighbors who are struggling to provide the electricity, and then it drives up the power prices in their own countries. So suddenly, the price goes up in Sweden for the Swedish users, right? And it's only because Germany buys the power, right? So there's a very complex system. It doesn't help anybody, the way it works.
Ronald, and this SUNF recycling is permitted, is prohibited. What's the logic for this?
Well, you can call it recycling. We have, I think, 90,000 pounds of it out there, and it's basically just be fuel for the next generation reactor. Elaborating on what Oliver mentioned, we're talking nameplate rating of wind and solar. It's a huge nameplate rating. The problem with the system is they don't work most of the time. The sun doesn't shine most of the time. The wind usually doesn't blow most of the time. And so, it's a redundant system to coal, natural gas, and nuclear. Here in California, we've shut down pretty much all of our coal power plants. So we have, when the wind and solar is not functioning, we import more electricity than any other state in the country. And we're importing electricity into California from coal-fired power plants on the other side of the border of California. We shut them down here, but we're importing the electricity from coal-fired power plants in Wyoming, et cetera, et cetera. So, it's just we're paying for two systems.
And is there storage of this product as UNF in the United States, for instance?
I'll let Steve and Oliver take that one.
Could you repeat that, Armando?
Storage of these products. Is there?
Okay,
storage?
they are very safely stored right now.
Oh yeah.
They were supposed to have been buried in a mountain starting in 1998, and of course the government did not hold up their end of the bargain. So technically, they're not collecting rates money from users like they used to produce the system because they don't have a system. And they are actually paying out of a legal settlement. They're paying about $1 billion a year for all the utilities, for all the spent fuel, about a little under $1 billion a year for them to store it on their facility. And still, the utilities don't like to do that. But it's very safely kept. The process is it comes out of the reactor. It's both radiologically and physically hot because you still have a lot of the fission products that are decaying. That's creating heat. So they move that. Of course, they move it all remotely and shielded into these big ponds of water. Well, water is very effective at shielding this radiation. Plus, it's very effective at taking away the heat. But after about 3 years, sometimes up to 5 years, depending on the burnup, it's now decayed so far that it can air cool. And so at this point now, they're supposed to go on off to the permanent repository, but now they have to put it in something called dry cask storage. And that's very efficient the way they're doing it. It's very, very safe. And there's no if you imagine a reinforced concrete container that they use to shield this thing, it's very difficult to imagine it being destroyed in an earthquake. Or transportation. You have to really, really try hard to get through this material to get into it. So it's very, very robust. And then some of them have been sitting there for like 30 years now on the pads, and nobody's bothered them. And they're basically on a pad behind a chain link fence and a little barbed wire. Nobody bothers to try to, because imagine how would you go about it? I've tried to say lots of people, if they were a terrorist, why would they choose this and how they go about it? And I never get an answer. Because there really is no logical reason why they'd ever use this as a method.
That's a good point. So there is no, safety and environmental concerns to use this energy.
There haven't been so far, and I can't imagine any that would come up. Although people try to think them up, there's no logical path of reasoning that brings you there. They're just trying to scare people. It's really is kind of a negative. A negative
propaganda
PR effort to try to scare people away from nuclear, when really this is the best deal in the world by far. It's really a no-brainer.
That's a good point, Oliver, because if you can use 97% of this energy that's still stored, not being used, so it's enough to the whole country. It's an easy mode. Is it correct?
Yeah, for centuries to come, right?
Wow.
And it's for the entire country. And then, of course, you have the depleted uranium, which is almost 100% uranium-238. And there's so much sitting around that you could power the country for thousands of years. So it is just a matter of implementing the right technology. And it is a breed and burn process in these new reactors. So they make fuel and it uses this up for energy production. And these reactors, they can sit there for decades and run the process. And the way you load up the spent fuel is literally you take the fuel pellets, which are like ceramics, little ceramic cylinders, and you take them out and you can say every shift puts in like a pound or 2 pounds of the stuff in the reactor to keep it going. Literally, you slowly put more in, right? I mean, it's like a dash of salt, right, in a reactor that contains 40 or 50 tons of the stuff already, and just to keep up with the burn up, you add a little bit, a pound or 2 here and there, to effectively keep the energy production going, and it will go for decades, right, that way. So it is it sounds very simple.
Sounds very simple.
One of the engineers who designed the system like that explained it to me. Literally, he said, those things are literally just sitting there producing energy, and all you do is you add some more of the spent fuel. You don't really need to do anything with the spent fuel itself. The 97% are
Wow.
totally usable, right, as
That's
it
a
is,
huge number.
right? Yeah.
It's a fantastic number. Ronald, comparing wind and solar power with nuclear, this kind of nuclear, 97% remaining energy, what are the environmental advantages or disadvantages of to use this nuclear energy?
They're tremendous. The reason we wrote this article about the nuclear waste, the slightly used nuclear fuel being a game changer, is it's going to allow us to generate continuous electricity, emission-free electricity, and very inexpensive electricity. And the best part of all is you're not going to mine for any of this material because it's already existing. It's slightly used. Versus wind and solar, we need lithium and cobalt and uranium and magnesium. We need all these exotic minerals and metals that are being mined throughout the world. And these are coming out of Earth's resources. And Earth's resources, our planet is 4 billion years old, and those resources are not being replenished. So if we take them out, we're not replenishing them. So that's another advantage of nuclear. We're not going to be extracting anything else out of the Earth's resources. We've already got that slightly used fuel that's available to generate this electricity. So I would think we've been subsidizing wind and solar. I think if anything, we want to subsidize private industry to maybe give them a kickstart, accelerate them to get this thing moving and get the Nuclear Regulatory Commission to, get their act together and let's start moving towards zero emission, inexpensive electricity. Also, the economies around the world need it. And, the fact that 80% of this world is living on less than $10 a day, they can't afford wind and solar electricity.
And Ronald, with the wildfire that we are having in California, no solar and wind energy are being produced, I suppose.
No, not in the populated areas. The wind and solar is in open space or California's close to the ocean, so a lot of it's offshore, which means, as all of Mitch, we're going to bring the transmission back to land because nobody's living out there; they're living over here.
Yeah. And as Oliver said, with a long lines to transmit all this energy and not short, it's a very big problem, really is. So, gentlemen, let me conduct to the conclusion. So, it's a game changer. Is it possible, feasible? The governments want to do that. What's the base for this transformation, Stephen Curtis?
So we have a pretty unique plan, and nobody else is in this space that we're thinking of. Everybody else wants to go cater to the federal government, convince them. We think that a state could take the lead in this, and it's up to us to convince them that there's an economic benefit, a moral benefit, and it's not detrimental to their state to do this. So we have to get out and talk to them and explain this to them. Basically, the idea is if they consented to accept slightly used nuclear fuel, then they could ask for all kinds of benefits from the U.S. government, because nobody will do that now. No state will consent to accept it. So the first one that puts that in place will be able to garner a whole lot of advantages. And they can ask for what they want to. We propose a series of let's build some reactors, let's build some tech transfer laboratories, let's build an industrial park and other things with this money from the spent fuel fund, which is $50 billion, and that's still quite a little bit of money, and then transfer the bulk of that to private industry. So we don't go on for 20, 30 years subsidizing this thing. You let the industry take it on, let them have their first of a kind reactors, let them have their facilities, and the state that does this can attract a lot of those companies to their state because that's where everything's being done. And other companies are going to be there. So the idea is if we can convince a governor to do that, there's a huge economic benefit to his state. And technically, this spent nuclear fuel, some people call nuclear waste. We call slightly used nuclear fuel. This stuff has never harmed anybody. It is harmful, but automobiles are harmful. Okay, so we can say anything is going to be harmful, but when we take the risk benefit, there's no comparison, and we understand how to handle this stuff. It's not liquid or gaseous. It's a ceramic pellet that we just handle inside of a concrete container. And when we remotely, if we deal with it at all, we deal with it remotely. We've been doing that stuff for ages without a single problem. And so there's really no technical reason why we shouldn't do this. And it's just a matter of convincing who can convince Washington to basically get out of the way. They're doing all they can to stop it. And we just have to, we don't need that kind of help. Private industry can take this on and do it. We just have to get them to not subsidize their competitors and to really actually let business happen.
Very good point, Ronald, because how can we make that the governments listen to these proposals?
Logic and reasoning would be the start.
But is it possible? You see that it's possible to talk to governments to convince them that to start these procedures?
I have high hopes, but knowing what the government does, it's amazing that it seems like I joke at times that you can't bring logic and reasoning into the conversation. Because if you do, then the main thing is you got to have conversations and find out why they're resisting it. There's so many benefits, as Steve and Oliver have talked about, that, you know, it's zero emission, it's unlimited amount of fuel, no more exploratory efforts to get it, and it's going to be great for the world's population. You know, my concern when I write my energy literacy articles is the fact that it's only the wealthy countries that have a green movement. Mm-hmm. But the wealthy countries only represent about 1 billion people. There's 7 more billion in this world that haven't joined the Industrial Revolution. Yeah. And if we can give them, you know, inexpensive or close to free electricity, it would basically improve their lives. And I think that would be a real game changer.
Yeah. Let me just point out, too, that this, if we use the spent fuel, it actually is renewable, okay? Because they're making new spent fuel all the time. And that's the definition of renewable energy, is that more is being made all the time. Now, they'll argue that that's not a natural process. But if you essentially has an unlimited supply already, and they're making more all the time, it's hard to say this isn't renewable. And that's what they're trying to do, is they're trying to call wind and solar renewable. And burning wood, they call that renewable. And they don't want nuclear in that bunch as part of the political facade that's being manifest now. And I really think there's a huge economic benefit to a state that wants to do it. I've been working on this for 8 years, and I've never seen more interest in it than there is now. We're finally getting people calling back. They're listening. They're reading Ron's and our articles, and they're reaching back, and they're hearing these podcasts, and they're reaching back. And that's the way it's going to work, because if I just say it's a good idea, it's probably not enough. But if 100 people say it's a good idea and they get the ear of some of these people, that could be enough. And this really is the biggest no-brainer out there.
Armando, Steve brought up a good point. The fact that we've got over 400 reactors out there now, they are manufacturing the fuel for the fast breeder reactor.
Yeah. Oliver, what's the probability between 0 and 100? How likely this solution be applied in the United States in the next 10 years?
Well, I'm sure somebody with some brains will pick up on it. I think there's enough states out there. There's a lot of interest out there. And I think there's 100% chance that these new technologies eventually come to the forefront, because there's so much energy left in these materials, right? Yeah. Now, the other thing, what I want to point out is, people might ask, what is a waste of the waste, right? You have nuclear waste, now you burn it up in a fast reactor. So what is a waste product of that, right? Uh-huh. So literally you're making about 30 elements it effectively goes back to the alchemists a couple of hundred years ago that tried to turn lead into gold. In this case, you turn uranium into gold, not literally, but you make elements like rhodium, which is in the platinum group. 1 ounce is about $5,000 right now. It's the most expensive precious metal that you can purchase. Now, those reactors make hundreds of ounces per ton for the nuclear fuel. And in addition to that, you make a whole bunch of rare earth elements. You make other elements that can be used industrial-wide. And the total value of when you turn the 90,000 tons of existing commercial nuclear waste into energy, the waste product is worth about $1 trillion. Just what, so the ashes are actually highly valuable, right? And it's much more valuable than the uranium itself. When you would sell the uranium pound by pound and on the market for uranium, you would get a lot less. You turn literally lead into gold from the process. It's just not lead and it's just not gold that comes out, but you have a process where you take something, make something extremely valuable from it, electricity, and then at the end you have precious metals and rare earths and other stuff left over.
And this solution is exclusive for the United States or for other countries the same?
Anybody can use that globally. Yeah, you can effectively turn the whole world into a place where people can live with almost free electricity. So,
and the value of the energy at 10 cents a kilowatt hour is $100 trillion. Now that boggles your mind. I mean, you think $1 trillion is $3,000 for every person in the United States. People don't internalize what that number is. But the value of this energy, just using the United States existing 90,000 tons of slightly used nuclear fuel at 10 cents a kilowatt hour is $100 trillion. Now, there's 270 years worth of the current, usage of that. So like I said, they're going to want to use that up as fast as they can. So you can imagine if you lower your electricity costs, how many more technologies come into vogue that you can use to help everybody along. I mean, you could charge cars right straight from the roads if you wanted to, because you really wouldn't care about the efficiency of electricity. You wouldn't waste all your time, retrofitting houses for insulation and everything like that, because you really would want these people to use more electricity so that we can, eventually dispose of the spent nuclear fuel, and they're making, 2,000 tons of it a year in the United States. So it boggles, like I said, it boggles the mind, the economics of this. And we just have to, I think, educate people. That's the basic bottom line, I believe.
And there's a lot of energy remaining. So it's not a small quantity, it's a huge quantity. It was a great pleasure having Ronald Stein, Oliver Hemmers, and Steve Curtis. Please stop the video later and see these bios. It's fantastic. Fantastic, guys. Thank you so much. Thank you.
Thank you very much, Armando. I really appreciate the discussion. Be talking to you soon.
Yeah. And take care, Ronald, with your problems in California.
California.
Anyway.
Bye-bye.
Bye.